This is the case for the Younger Dryas Impact Hypothesis, a cosmic impact 12,900 years ago proposed by researchers like Richard Firestone and James Kennett. It's built not from theory, but from anomalies found in the dirt. Materials that, by the standard rules of geology, should not exist where they were found. They're buried in a thin sedimentary layer across 4 continents, in sites separated by oceans, dating to exactly the same moment in deep time. Some of these anomalies are still considered evidence today. Others have been overturned. But the layer itself is real, and what's inside it is the closest thing Earth science has to a crime scene from the end of the last ice age. The Younger Dryas was a sudden, violent cold snap that began roughly 12,870 years ago. Temperatures in Greenland dropped by more than 15 degrees Celsius. The warming trend that had been ending the ice age reversed almost overnight, and 1,000 years of cold followed. In North America, the massive Laurentide ice sheet covering the continent was fed by Lake Agassiz, a glacial lake larger than all the Great Lakes combined. At least 35 species of large mammals vanished. Mammoths, mastodons, giant ground sloths, dire wolves. An entire archaeological culture, the Clovis people, disappeared with them. The mass extinction event that bracketed this transition is one of the most consequential in human prehistory. The Younger Dryas Impact Hypothesis proposes a single cause for all of it, a fragmented comet or asteroid, possibly from the torrid meteor stream associated with Comet Encke, that detonated in the atmosphere, scorched the continents, melted the ice sheets, and disrupted the thermohaline circulation that triggered the cooling that followed. The hypothesis is controversial. The evidence for it is anomalies in the ground, and they're the subject of this archive. The first anomaly is a black layer. At more than 50 archaeological sites in North America, including famous Clovis locations like Murray Springs and Blackwater Draw, geologists have documented a thin band of carbon-rich sediment, sometimes only a few centimeters thick, sitting in the soil at exactly the depth that corresponds to 12,900 years ago. This is the black mat. It contains charcoal, soot, and biomass burned at high temperature, and it's visible to the naked eye. Beneath the black mat, archaeologists routinely find the bones of extinct Pleistocene megafauna alongside Clovis spear points. Above it, nothing. The animals and the tools don't appear in the layers that come after. Whatever happened at the level of this dark line, and the species and the culture that flourished beneath it didn't survive it. The mainstream interpretation is that the black mat is a record of environmental change. Widespread fires, then standing water and wetlands as the climate cooled. The disputed interpretation is that it's the residue of something that fell from the sky. The second anomaly sits directly beneath the black mat. It's a thin sedimentary layer, usually less than 5 centimeters deep, that contains an unusual concentration of magnetic microspherules. These are tiny, perfectly spherical droplets of melted iron-rich material, the kind of formation you get when something flash melts and then cools mid-air. Microspherules of this exact type have been documented at the Cretaceous-Paleogene boundary, the Chicxulub crater layer that records the asteroid impact that ended the dinosaurs. Finding them in another thin, continent-spanning sediment band is the kind of pattern that catches a geologist's attention. Critics argue these microspherules occur naturally in many sediment layers and aren't unique to the Younger Dryas boundary. Proponents, including the Comet Research Group, have documented peak abundances of them at the boundary across more than 50 sites and counting. The third anomaly is harder to explain by any natural process the planet typically produces. Inside the same boundary layer, researchers have reported finding nanodiamonds. These are microscopic, crystalline carbon structures that form only under extreme heat and pressure. Some of them are described as hexagonal nanodiamonds, also called lonsdaleite, a polytype that requires shock pressures normally associated with impact events. A 2012 study of sediment cores from Lake Quetzeo in central Mexico identified 3 different types of nanodiamond at the Younger Dryas boundary. A study at Lommel in Belgium identified cubic diamond nanoparticles in the same layer. The reported global distribution of nanodiamonds is one of the central pillars of the impact case. It's also one of the most contested. Multiple peer-reviewed studies have argued the nanodiamond identifications are mistaken, that what was reported as hexagonal diamond was actually a different carbon mineral, or that the carbon structures involved are misidentified fungi, insect fecal pellets, or fragments of older organic material. The science here is unresolved. What you can say with confidence is that something carbonaceous and unusual is concentrated in the boundary layer at multiple sites. What that something actually is depends entirely on which laboratory analyzed it and which technique they used. The fourth anomaly is harder to dismiss. At Abu Hureyra, a prehistoric village in northern Syria, the Younger Dryas boundary layer contains meltglass. This is silica-rich material that has been melted and rapidly cooled. The meltglass at Abu Hureyra makes up about 1.6% of the sediment by weight, which is an extraordinary concentration. When researchers analyzed the temperatures required to form it, the numbers came back somewhere between 1720 degrees Celsius and over 2200 degrees Celsius. For context, a hut fire reaches between 11 and 1200 degrees. Lightning strikes leave behind a distinct magnetic signature in the glass they form. The Abu Hureyra meltglass shows none of that signature. Volcanic glass typically contains a measurable percentage of water. The Abu Hureyra meltglass contains almost none. Its water content is between 2 and 0.05%, which is the same range you find in tektites, the glass droplets produced by cosmic impacts. The temperatures and characteristics are reminiscent of what was observed at the Tunguska event of 1908, where an atmospheric explosion created similar thermal effects across hundreds of square kilometers. A 2023 study went further. Researchers at Abu Hureyra examined quartz grains from the same boundary layer and reported finding shock-fractured quartz. This is a low-pressure form of shock metamorphism that, based on near-surface atomic airburst experiments, can be produced at pressures under 8 gigapascals. Shocked quartz is one of the strongest accepted indicators of a cosmic impact. Its presence at the Younger Dryas boundary, if the identification holds up, would represent a significant strengthening of the impact case. Independent researchers haven't yet confirmed the finding at other sites, and the question of whether the fracturing at Abu Hureyra is truly shock-derived or instead the product of some other high-energy event remains open. The fifth anomaly is also the most recent to be overturned. In 2013, a team analyzing an ice core from Greenland's GISP-2 project announced the discovery of a sharp spike in platinum dated to approximately 12,800 years ago. Platinum is rare in the Earth's crust and far more common in meteoritic material. The spike was widely interpreted as a chemical fingerprint of the proposed impactor, a fragment of a comet or asteroid that had vaporized in the atmosphere and rained its trace metals over the ice sheet. For more than a decade, the platinum anomaly was one of the most cited pieces of evidence in the impact case. That changed in 2025 and 2026. A new study led by volcanologist Charlotte Lindqvist examined the geochemistry of the platinum spike in detail and reached a different conclusion. The signature, the team reported, more closely resembled volcanic gas condensates from submarine and subglacial fissure eruptions than it did extraterrestrial material. The spike lasted approximately 14 years, which is difficult to reconcile with an instantaneous cosmic event. Updated ice core dating also placed the platinum signal roughly 45 years after the Younger Dryas cooling began, which means it likely occurred too late to have caused it. The most probable source, the new analysis suggests, is a fissure eruption in Iceland, the kind of slow, sustained volcanic event that the geological record of the North Atlantic shows happens periodically. The platinum spike, in other words, may have been pointing at something real and dramatic, just not the thing it was originally thought to be pointing at. That brings us to the missing piece. If a cosmic impact actually occurred 12,900 years ago, somewhere on Earth, there should be a crater, or, in the case of an airburst, a structural disturbance large enough to be detectable. Some researchers point to the approximately 500,000 elliptical Carolina bays scattered along the Atlantic coast as potential secondary impact features, though this connection remains hotly debated. For a brief window between 2018 and 2022, it looked like that crater had been found. A 31-kilometer impact structure buried beneath the Hiawatha Glacier in northwestern Greenland was identified using ice-penetrating radar. The discovery was published in 2018, and the geological context, the disturbed ice layers above it, the proximity to the platinum spike, the sheer size of the depression, led some researchers to suggest a possible Younger Dryas age. For the impact hypothesis, the Hiawatha crater was, in the words of one geologist, the long-sought smoking gun. In 2022, two independent teams dated the crater. One used uranium-lead dating on zircon crystals from the impact debris. The other used argon isotope dating on melted sand grains. Both methods return the same age, approximately 58 million years old. The Hiawatha impact predated the Younger Dryas by a factor of more than 4,000. It was a real impact crater formed by a real asteroid, but it occurred during the Paleocene, long before there were ice sheets in Greenland and long before there were humans anywhere. The smoking gun turned out to belong to a much older crime scene. Today, no impact crater has been confirmed to date to 12,900 years ago. Proponents of the hypothesis argue the proposed event wasn't a single large impactor, but a fragmented one, multiple smaller airbursts and ground impacts distributed across continents, most of which wouldn't leave detectable craters. Critics argue the absence of a crater, combined with the unresolved status of the nanodiamond and microspherules evidence, means the case hasn't been made. A comprehensive 2023 scientific review concluded the Younger Dryas Impact Hypothesis hasn't converged into a self-consistent scenario that satisfies orbital mechanics, impact physics, geology, and paleoclimatology simultaneously. And yet, the boundary itself remains. The black mat is real. The meltglass at Abu Hureyra is real. And the temperatures required to produce it are real. The boundary layer continues to appear at archaeological sites on multiple continents, in the same thin band of sediment, dating to the same approximate moment when the climate collapsed and the megafauna disappeared. The independent researcher Randall Carlson has spent decades documenting the geological signatures of rapid, catastrophic flooding at the end of the last ice age. The scablands of eastern Washington, the meltwater channels carved across North America, the abrupt sea level pulses that drowned vast continental shelves. The Younger Dryas event happened. Something extraordinary occurred at the moment it began. The question of whether that something fell from the sky remains unresolved. What the evidence shows, taken together, is a planet that records a violent transition in its geology, its chemistry, and its biology 12,900 years ago. A thin, dark line in the soil, tiny iron spheres melted in mid-air, glass that requires temperatures hotter than any fire on Earth could produce, quartz that may have been shocked at airburst pressures, a platinum signal that's now been reinterpreted, and a crater that turned out to be far too old. The data is fragmentary and contested, but the layer is there. The extinction is there. The cooling is there. And the search for what caused them isn't over. This is what the dirt is saying. The interpretation is still being argued. The anomalies are not.